The last thing I want to talk about is that these limits as x goes to plus or minus infinity of our rational function would work with some other functions as well. So there are functions, the argument is simply an argument for growth, which one grows faster. And so if we have a rational function, I guess technically a polynomial is a rational function whose denominator is 1. You can do the same thing with a polynomial function. If we have a ratio of exponential functions to polynomials, well, the exponential function grows faster than the polynomial. So I could do the same similar argument of whether the limit is 0 or whether the limit is infinite. And so a lot of functions that are like rational functions can be evaluated using the same understanding. Let's look at example 6. These are similar to rational functions, but they're not exactly rational functions because it's not polynomial divided by polynomial. I'm going to find the limit as x goes to infinity of this w of x and the limit as x goes to infinity of this j of x function. Let's begin with wx, and in particular, the limit as x goes to infinity of w of x. So remember, we're looking at growth rates. And so if you look at the growth rate on the top as x goes to infinity, the top is dominated by the 9x portion of the 9x minus 3. As we look at growth rates, we're going to look at the fastest part of the growth on top, that's 9x. And then we're going to look at the most significant part of the growth rate on bottom. In the denominator, we have the square root of x to the 4th minus 5. This minus 5 is not going to contribute very much when you get really, really big values of x. And so that bottom is kind of like the square root of x to the 4th. Now, that function, 9x over square root of x to the 4th, well, square root of x to the 4th is just like x squared, right? This is the positive square root of x to the 4th. So as you plug in values, you get that. And notice what we have. We have a rational function, 9x over x squared, that I can simplify, or I can just notice that the denominator has higher degree than the numerator, and so I get 0. One thing we do need to be careful of, as we have really big values of x, doesn't make sense to plug those values in here. And it does make sense. You could plug in values that are really big x's. The same thing holds true as x goes to negative infinity. As x goes to negative infinity, we can do all of these same things. And you can plug in negative infinity into this negative infinity to the 4th. You'll get a positive number, and then you're square rooting a positive. So it's going to be the exact same thing. And once again, because the denominator has a higher degree than the numerator, that limit is also 0. So as x goes to infinity and as x goes to negative infinity, our w of x is 0 because of understanding the limits of rational functions. So even though this is not rational, it's kind of like a rational function, and then we can find the limits. The other function that we want to figure out is j of x. And in a similar way, we can focus on the main aspects of the numerator and denominator. The numerator, well, square root of x is taking control. That's the only thing in there. The denominator, when x gets really, really big as a positive value, this plus 8 is not going to contribute much. So this is going to just be 7 times the square root of x in the denominator. Well, square root of x and square root of x, those can be canceled. This is just like having x to the 1/2 power divided by x to the 1/2 power. So essentially, we have the same degree, although they're both to the 1/2 degree. And we can say, therefore, that limit is 1/7. So same degree, so the limit is 1/7. Now, here's the thing you have to really watch out for. In this case, you can't say the limit as x goes to negative infinity is 1/7, because as x goes to negative infinity, you're plugging in really small numbers. And that means the numbers you're plugging in are negative. Well, the domain of j of x does not allow you to plug in really big negative numbers. So this limit does not exist since you cannot plug in negative numbers, which are really big. Just say big negative numbers. That's not real well defined, but you guys understand what I mean by that. Big in terms of absolute value, but negative. So you do have to be a little bit careful about that. Make sure your domain works with x going to negative infinity, especially when you have square roots around, because sometimes you can't have a square root of a negative. So there we go. That is the end of looking at limits, either going to infinity or limits as x goes to infinity.